Greetings. Finally, today we are going to finish up Chapter 9. It's a long chapter. We are in the section now that is talking about conditional probability. And there's some interesting things that come out of this. There's something called Bayes' theorem. We'll be taking a look at all of this. Anyway, the idea of a conditional probability means that we are performing an experiment, but we're actually given some information about the outcome before we're asked to calculate a probability. So let's consider an example. Suppose we're going to roll a fair die. Okay, so remember what it means when we say that the die is fair. That means that the probability of 1 is equal to a probability of 2. All of these are equal probabilities, and that's equal to 1/6. Okay, now I could certainly ask the question like the following. I could say, what is the probability that we rolled a 4? And again, we just note that there's a uniform probability here, and we would say, well, the probability of rolling a 4 is just equal to 1/6. But now let me give you a little more information. Suppose I were to ask you the following. What is the probability that I rolled a 4 if it is given I rolled an even number? Okay, so the key point here is, as I say, if it is given, okay, and that's what's called a conditional probability. In other words, if I come over here and I say, let B be the event I rolled a 4. And I say, let A be the event I rolled an even number. Then the way that we would denote this over here is we would say, what is the probability of B? And then we draw this vertical line here and we say A. And this is read, what is the probability of B? What is the probability of B given A? And this is what's called a conditional probability, right over there. Okay, so let's think about this a little bit more. Okay, so we know that the probability of rolling a 4 is equal to 1/6. And we know that the probability, well, what's the probability of rolling an even number? Well, we know that the set of even numbers that I could roll on a die would be 2, 4, and 6. And we know that the actual sample space is 1, 2, 3, 4, 5, 6. Okay, so we know that the probability, we can see right here, the probability of rolling an even number would just be 3/6. The probability of E would just be 1/2. Okay? Now, if we go back to our previous example and we say, well, what's the probability of B given A? And remember, that was the probability of a 4 given an even number. This is, by definition, the probability of B intersection A over the probability of A. And let's think about what that's saying here now. What we're saying now is when I have a conditional probability, I am reducing the size of my sample space. In other words, initially, if I just ask about the probability of rolling a 4, we're considering a sample space S where I could have these six outcomes. But now when I say, well, what's the probability of 4 given an even number, what I'm doing here now is I am reducing my sample space now down to something smaller. So the probability of B intersection A over the probability of A, well, think about what that would be. I'm reducing myself down to this sample space here, and I'm asking what is the probability of rolling that? Well, I have 3 elements in here, and the probability of rolling the 4 would just be equal to 1 over 3. Notice that that's different than the answer we had right over here, where we just said that the probability of B was equal to 1/6. Okay, so this is what's called the conditional probability. Okay, conditional probability means I'm given some extra information. The extra information is right over there. That's the extra information. And what normally happens here is when I am provided this extra information, that says to me that I've reduced the size of my sample space. Okay, and in this case, the sample space went from 6 possibilities down to 3 possibilities. Now, let's consider an example out of your book. Okay, and again, this goes back to rolling die. And your author talks about rolling 2 dice, or he says the dice have different colors. But he asks, what is the probability? So I'm going to roll 2 dice. And the question is, what is the probability that the sum of the dice, that the sum is 8, but now here comes the restriction, given that both dice were even. Okay, so let's think about a couple of things here. First of all, why don't we could think of this, we have a tuple, and this could be the output of die 1, and this is the output of die 2, and we know that there are 6 possibilities over here, and there are 6 possibilities over here, so if I'm keeping track of the output of 2 dies, there are a total of 36 possibilities, each one equally likely. Okay, so the probability of an 8, well, let's think how the different ways that I could get an 8. I can get an 8 with a 2 and a 6, a 3 and a 5, a 4 and a 4, a 5 and a 3, or a 6 and a 2. These are the ways that I can roll the 2 dice, and the sum is going to come up to 8. So there are a total of 5 possibilities here. So the probability of an 8 would just be 5 over 36. If I want to consider what is the probability both are even, well, again, let's start counting the ways that we could do this. Well, there could be a 2, a 4, or a 6 over here, and there could be a 2, a 4, or a 6 over here. So in other words, if I wanted to list them all, it could be 2, 2, 2, 4, 2, 6, 4, 2, 4, 4, 4, 6, 6, 2, 6, 4, 6, 6. But we see that there are 3 ways to do it this way, 3 ways to do it this way, a total of 9 ways to do it. So the probability that both are even, this is going to equal 9 over 36. So now, if we want to calculate the probability, what is the probability that we rolled an 8, given that both dies are even? That's going to equal the probability of 8 intersect both are even over the probability that both are even. Well, let's see if we can figure this out. The probability of 8 and both are even. Well, here's the probability that they're 8, and the probability that both are even. Look, I've got that one, they're both even. That one over there, they're both even. That one over there, they're both even. Okay? So the probability that I get an 8 and both are even would just be 3 over 36. Okay? And the probability that both are even is just 9 over 36. These 36's cancel out, and 3 over 9 is equal to 1/3. Okay? Not too complicated. A couple of things to note here. Again, these are right in your book. This is just manipulating formulas. So we have the probability of B intersection A is equal to the probability, or B given A is B intersection A over P of A. If I multiply both sides by P of A, that gives us another formula here that we'll find useful. The probability of B given A times P of A is equal to the probability of B intersection A, just like that. And another useful formula is the probability of A is equal to the probability of B intersection A over the probability of B given A. Okay, so we're going to find all three versions of this equation very, very useful for us in the rest of this section.
It certainly is a big bun.
It's a very big bun.
Big fluffy bun.
It's a very big fluffy bun.
Where's the beef?
So let's continue along considering an example from your book. Your book says, suppose that we have an urn. It could be a bag. It could be anything you like. So here's our urn over here. And there are some colored balls in there. And we want to assume, in fact, that there are 5 blue colored balls in here. And we want to assume that there are 7 gray ones. Okay? And what we're going to do is we are going to pick 2 balls, okay, without replacement. Okay, so we want to note a couple of things. We want to figure out a few things here. We want to figure out what is the probability that we had a blue, and then your author just says, let's say, a not blue. Or let's talk about having a not blue and a blue. Or let's have a not blue or a blue blue. Okay, now the reason why he picked not blue will become apparent in a second. He could have, of course, just said gray. We want to talk about what are these 4 probabilities here. So your author says, let's do the following. Let's adopt the following notation. We'll let B1 equal the event that the first ball is blue. So, of course, if we do that, then we would say that B1 complement is the event that the first ball is not blue. And we're going to do the same thing. We're going to define this thing. B2 would be the event that the second ball is blue, and we would have that B2 complement is the event that the second ball is not blue. So when we're talking about figuring out the probabilities of these things, what we're actually being asked to figure out is what is the probability of, say, B1 intersection B2. That would, of course, correspond to the event blue, blue. But then we're also being asked to figure out the probability of B1 intersection B2 complement. We want to talk about the probability of B1 complement intersection B2. And we want to talk about the probability of, what have I forgot here? B1 complement intersection B2 complement. We want to talk about how to figure these four things out. And obviously, this may involve some conditional probability. So let's think about a couple of things here. So in our original urn, let's see, there were 5 blue and there were 7 gray. Okay, now I think that you're all willing to believe that the probability that the first ball would be blue, well, there are a total of 12 balls in here, and 5 of the balls are blue, so the probability of B1 would just be 5 over 12, and the probability of B1 complement would just be 1 minus 5 over 12 is equal to 7 over 12. Okay, so now what I want to do is I want to ask, what is the probability of B2 given B1? Well, first of all, if B1 has occurred, then that means that we picked the blue ball out of here, and we're now in the case where I've got 4 blue and I've got 7 gray. So now we're asking, in this situation here, remember we've been told that this occurred, and that is saying that we're in this situation over here. What is the probability now of picking a blue ball? And the answer here would just be 4 over 11. And by the way, this is very important. I want you to note that in your book there is a misprint. In the book, they say this is 1 over 11, and that is clearly wrong. So, and then if this is 4 over 11, then, by the way, the other thing that we would get here is we would get that the probability of B2 complement, given B1, well, if I'm in this situation over here, what is the probability of not picking a blue ball, or in other words, picking a gray ball? Well, that would be 7 over 11. Everybody okay with that? But now we get to use these formulas that we had before. Yes, I know formulas hurt sometimes, but sometimes they're very useful. Okay. Remember what we said over here, that the probability of B2 given B1, well, that's equal to the probability of B2 intersection B1 over the probability of B1, and if we multiply both sides by B1, then we get that the probability of B2 given B1 times the probability of B1 is equal to the probability of B2 intersection B1. But let us recall, do I have it here? Yes, I do. These were the various probabilities that I actually wanted to calculate. So that if I wanted to come over here and say, okay, what is the probability of B2 intersection B1? And remember, that would be, what is the probability of drawing a blue ball on the first time and a blue ball on the second time? Well, according to that, that is equal to the probability of B2 given B1 times the probability of B1, and that is equal to, well, the probability of B2 given B1 is 4 over 11, and we said the probability of B1 is 5 over 12. So 4 times 5 is 20, and let's see, 11 times 12, well, 12 times 12 is 144, so I take away 12 from that, and that would be 132. And that's our answer to that one right there. Likewise, if I wanted to calculate what is the probability of B2 complement intersection B1, okay, we could calculate that too. Well, that's just going to be equal to, here's the probability of B complement 2 given B1, that's 7 over 11, times, and then we'd have to go the probability of B1, that's 5 over 12, and that's equal to 35 over 132. Okay? Does everybody see where this came from? Okay, that's just the probability of B2 complement given B1 times the probability of B1. And when you take a look in your book, you can see that your book goes through the other cases as well. In other words, there were 4 different numbers here that they ask you to calculate, and I've just shown you how to do 2 of them. You should go ahead and do the other 2 for practice. And then the other thing that you should notice that's very interesting, so you'd have 4 numbers. You'll note that if you add all of those 4 numbers up, that they'll add up to 1. Okay, so now we are going to look at this thing called Bayes' theorem. And what's going to happen here, at first this is going to seem easy, then it's going to look hard, and then I'm going to explain to you that it's really easy. So watch closely. So here is the thought experiment that your author asks us to consider. So we have 2 urns here. Here's urn 1, and urn 1 has 3 blue balls in it, and it has 4 gray balls in it. And now we come over here, and here is urn 2, and urn 2 has 5 blue balls in it, and it's got 3 gray balls in it. And what happens is the following. We pick an urn at random, and pick a ball. And we note that the ball is blue. So the question is, what is the probability that we picked urn 1 given that the ball is blue? What is this? Okay, so let's get some notation here. Why don't we let B1 equal picked urn 1? Why don't we let B2 equal picked urn 2? And why don't we let A equal pick the blue ball? So what we're being asked to calculate here is we're being asked to calculate what is the probability of B1 given A. And the answer is I don't know. Well, let's start writing down things that I do know. Okay, for example, what would P of A given B1 be? Well, that's not too bad. If I have picked urn 1, so I'm over here, what's the probability of picking a blue ball? Well, there are a total of 7 balls in here. 3 of them are blue. That would be 3 over 7. That was easy. Then we're told we have 2 urns and we're picking them randomly. So we know a couple of other things here. We know that the probability of B1 is equal to the probability of B2. And that's equal to 1/2. Okay, so we know these quantities right over here. So let's start thinking about this a little bit more. Well, the probability of B1 given A, that's equal to the probability of B1 intersection A over the probability of A. And I look at this and I go, this might be something that I could use here. Okay? Let's just look at this for a second. We're going to need a little more boardroom here to figure these all out. Specifically, just give me a moment here to readjust things. We have these two quantities to calculate here. This one here and this one here. For the numerator here, this probability of B intersection A1, well, I want you to note that that part, that's equal to P of A intersection B1. Okay, when we compute the intersection of two sets, it doesn't matter what order we do it in. And we know from our definitions before that that is P of A given B1 times P of B1. Okay, here I'm worried we might be running off the end of the sheet, so let me get us some new blackboard space here. I'm going to bring this down here. Okay, so remember, our goal here is we're trying to calculate P of B1 given A. And we're saying, well, that's equal to P of B1 intersection A over the probability of A. And here's the first thing. So what I'm going to do here, again, I want to look at the top and the bottom. When I look at the top, I note that the P of B1 intersection A, that's just equal to P of A intersection B1. And by definition, that's P of A given B1 times P of B1. Just go back and look at the definitions there and we'll see that. Now, here's the tricky part. What is P of A? Well, see here, remember what's going on here is, you could almost think of, here's my sample space, and here's B1, and here's B2. So remember what's going on is we're saying, over here we're picking an urn. This would be that I pick urn 1, this would be that I pick urn 2. And over here, this is my event A. So we know that A is made up of two disjoint parts. A is made up of A intersection B1, and then it's also made up of A intersection B2. In other words, A is equal to A intersection B1 union A intersection B2. I hope that's all clear because we're going to generalize that in a moment. So the probability of A is, and notice that these sets are of course disjoint, okay, because B1 and B2 are disjoint. So the probability of A is actually equal to the probability of A intersection B1 plus the probability of A intersection B2. But again, this by definition, this is just P of A given B1 times P of B1 plus the probability of A given B2 times the probability of B2. So that if we come over here and I want to calculate, here's the big mess, the probability of B1, and let's remember what that is. B1 is that we picked urn 1, given that we picked a blue ball. That is equal to, well, the numerator we just said is this thing over here, over P of A given B1 times P of B1 plus P of A given B2 times P of B2. And these are all numbers that we know. Let's see, P of A1 given B1 P of A given B1 is 3/7. P of A given B1 is 3/7. So this is equal to 3/7. The probability of picking that urn is 1/2 divided by, so this is going to be 3/7 times 1/2 plus the probability of picking a blue if we picked B2. If we picked B2, the blue is 5/8 times 1/2. So we just have to go ahead and calculate whatever these numbers are. That's 3 over 14. In the denominator, we have 3 over 14 plus 5 over 16. And I leave it to you to pull out your calculators and find out what that is. Okay, so your author finishes up this section by giving you a very messy looking formula, and I'm going to give it to you as well, but before I present it to you, I want you to consider something else here. So we're going to draw a picture. Let's suppose this is my sample space right here. And let's suppose that my sample space is broken up into 9 pieces. So there are the 9 pieces there. And I want to assume that this is B1, and I want to assume that this is B2, and here's B3, B4, B5, B6, B7, B8, and B9. So first of all, I want you to notice the following, that BI intersection BJ is equal to the empty set if I doesn't equal J. The other thing that I want you to notice is that B1 union B2 union all the way up to B9, that's equal to S, the sample space, so that we know that the probability of B1 plus the probability of B2 plus, if I add all these probabilities up, B9, this is equal to the probability of the entire sample space, and that's equal to 1. Okay? Now what I want you to assume is, maybe I should even change colors here. So let me do that. Okay? I want you to assume that I have okay, this is my set A. I'll write it as a big letter here. So there's A. Okay, and I want you to notice that A is actually made up of 9 different parts here. It's actually made up of A intersection B1, and it's made up of A intersection B2, A intersection B3, so that if I come over here, I can actually say that A is equal to A intersection B1 union A intersection B2 union, and I can do this all the way down here to union of A intersection B9, just like that. Okay, so you'll notice a couple of things. Each one of these individual things here, they are disjoint. In other words, this set right here is disjoint from this set here, is disjoint from this set here, from this set here, from this set here. And so I could say that the probability, the probability of A is equal to the probability of A intersection B1 plus the probability of A intersection B9, like that. And in fact, I could even write this in a fancy way, is equal to the summation from I goes from 1 to 9 of the probability of A intersection B sub I. Everybody okay with that? So now I want to consider the following. Suppose I wanted to ask the question, what is the probability of, I'm going to say B sub 4 given A? Now, we can think about graphically what this thing is. First of all, remember what this is saying. If I'm saying, what's the probability of B4 given A? That says I'm given A. I'm given that this red circle has occurred. Okay? And now if I'm saying, given that that's occurred, what's the probability of B4? What I'm basically asking for, if you think about it, would just be the ratio of this area right here divided by the area of all of A. Okay? But here's the thing to notice here, okay? The probability of B4 given A is going to equal the probability of A given B4 times the probability of B4, okay, over the probability of A. Now that may not be clear. In fact, I don't like the way I said that. Let's come over here and say that this is going to be equal to the probability of B4 intersection A. I'm making all sorts of mistakes here. I do apologize. Let's start this all over again. All right, I think I'm ready to start again. So the probability of B4 intersection A, well, that's equal to the probability of B4 intersection A, and that's divided by the probability of A. Okay? Well, the probability of B4 intersection A is this, okay? Go back to our original definition of conditional probability, and you'll see that these two numerators are equal, okay? But now, this is equal to the probability of A given B4 times the probability of B4. And now, I want to come back over to here. The probability of A, this is just equal to the summation of the probability of A intersection BI, where the summation occurs over I. And now we're ready to get to our big result here. Namely, that the probability of B4 given A is equal to, well, let's remember, it's the probability of A given B4 times the probability of B4. And this was divided by the summation from I goes from 1 to 9 of the probability of, maybe we need to go back to the last slide just to remind ourselves, A intersection BI but that's equal to the probability of A given B4 times the probability of B4. And now we will invoke Bayes' rule again, and that's the summation from I goes from 1 to 9 of the probability of A given BI times P of BI. And this is the big important formula, and of course what makes it even bigger and more important is if I just get rid of the 4 and generalize that to some k. And I say something like the following. I say that P of A given B sub k times P of B sub k, all divided by the summation from I goes from 1 up to n, okay? And now, n isn't 9, it could be any number, p of a given b sub I times p of b sub I. And this would be the probability of a given b sub k. Oh no, I'm sorry, that's incorrect. One minute here, and we'll get it right. This is the probability of b sub k given a is equal right over there, where 1 is less than or equal to k is less than or equal to n. Okay? This is Bayes' formula right here. So if you want to consider this in a slightly more complicated example than what we did before, imagine instead of having 2 urns, we had 3 urns. Okay, so B1, B2, and B3 would be the events of either picking urn 1, urn 2, and urn 3. We could imagine that there's a mix of blue and gray balls on each one of the 3, and A is the event that we picked a blue ball. So you could ask the question, what's the probability I picked urn 3 given that I saw a blue ball? Or what's the probability that I picked urn 1 given that I saw a blue ball? And using this formula right here, I can go ahead and calculate it. In fact, I could assume that there are 4 urns or 10 urns. Okay. Your author gives a medical example that is very telling, very useful, and in fact, Bayes' theorem comes up a lot in medical settings. So what we want to assume is that there is a disease, we'll call it disease D, that has a probability of 5 out of 1,000 people in the general population get it. Okay? So in other words, the probability of D is equal to 0.005. And medical researchers have developed a test for this disease. So there is a test for the disease. And you can imagine this could be a blood test, it could be anything. But the problem in tests is that you sometimes get what are called false positives, and you also get what are called false negatives. So a false positive would mean that the patient tests yes for the disease, but doesn't have it. And a false negative would be that the patient tests no for the disease, but has it. And false negatives and false positives are a way of life. This is true of just about any medical test that you would have. So why don't we assume that for our test here and for our make-believe disease, that the probability of a false positive is 0.03. And why don't we assume that our probability for a false negative is 0.01. Now remember what this is saying. This would mean when we're saying this would be the probability of yes given no disease. And this over here, so that's what this is equal to, and what this is equal to here, this is the probability of a no given disease. Okay? False positive, false negative. So now the question, pick a person at random. Okay, they test positive. And the question now becomes, what is the probability they have the disease? So let's think about what this is asking here. This is asking what is the probability of the disease given yes. Okay? All right, so let's figure this problem out. First of all, let's try and write down everything that we know. So we know that the probability of the disease is equal to 0.005. And we also know that the probability of yes given no disease given, I'm going to write DC, disease complement, meaning no disease, that is equal to was that 03 or 003? That's 0.03. Okay, remember these were the false positives. Okay, the probability of a no, given that they had the disease, was equal to 0.01. These are the false negatives. By the way, these two pieces of information let us figure something out. So if the probability of a yes, given that you don't have the disease, is 0.03, then the probability of a no, given DC, is equal to 0.97. And the probability of a yes, again looking at this, the probability of a yes, given that you have the disease, is equal to 0.99. Okay, you see how we derive these two numbers from these two numbers right over here. Okay, so what we're asked to do, what is the probability of a disease given yes? Okay, and by Bayes' rule, we know that that's going to be equal to the probability of a yes given the disease times the probability of the disease, and that's going to be divided by the probability of yes given the disease times the probability of the disease plus the probability of yes given no disease, or the disease complement, times the probability of the disease complement. Okay, this is just Bayes' formula right over here. So I think that these are numbers that we all have. The probability of a yes given the disease is 0.99. The probability of the disease is 0.005. And that would be divided by 0.99 times 0.005 plus the probability of a yes given no disease. So the probability of a yes given no disease, that's 0.03. See, probability of yes disease complement, that's right over here, times the probability of disease complement. So the probability of not having the disease would be what? Well, if the probability of having the disease is 0.005, then the probability of not having the disease is 0.995. Right there. And let's see, according to your book, I think these are the same numbers we have over here. The probability is about 14.2%. Thus, the probability that a person with a positive test result actually has the disease is 14%. Let's go back to where we were. So this is approximately 14%. That doesn't sound too good to me. And that just goes to show you that these numbers over here in and of themselves don't tell you the complete story. Okay? This is a very instructive example, and I suggest that you look at it closely. Finally, we finish up this entire chapter with a very simple idea, the idea of what are called independent events. And we'll do this by way of an example. Why don't we imagine that we're going to flip a fair coin twice. Now let's remember what this means. Fair means that the probability of heads is equal to the probability of tails, and that's equal to 1/2. And why don't we let A be the event? The first flip is heads. And why don't we let B be the event? The second flip is heads. Now the whole idea of independence here informally is the following. We can imagine that we record this as a tuple right there. So this is flip a fair coin twice. We record the events for the first flip here and the second event there. The idea of being independent is that the probability of what happens over here has nothing to do with the probability of what happens over here. We can say the converse is true as well. The probability of what happens here has nothing to do with the probability of what happens over there. So in fact, we could say something like the following. We could say that the probability of A given B should just be equal to the probability of A. It has nothing to do with B. Likewise, the probability of B given A is just equal to the probability of B. Okay? But let's just look at this a little bit. The probability of A given B, that's the probability of A intersection B over the probability of B, and we're just saying that that's equal to the probability of A. And now multiplying both sides by the probability of B, that just tells us that the probability of A intersection B is equal to the probability of A times the probability of B. And that is our definition right there of independence. Okay? So if the probability of heads is equal to the probability of tails is equal to 1/2, then the probability of getting a head and a head would just be 1/2. 1/2. I think that's pretty straightforward, pretty easy to see. It's easy to construct other things. Suppose I'm going to do an experiment which consists of flipping a coin. And I'll say a fair coin. And suppose we're going to roll a die. Roll a fair die. And we ask, what is the probability of a head and a 6? Well, we recognize that these are completely independent events, and that should be the probability of a head times the probability that, which would be 1/2 times 1/6, is equal to 1/12. Okay? On the other hand, consider an urn. So here's our urn. And suppose there are 4 red balls in it, and suppose there are 6 gray balls in it. Okay? And you ask, what is the, I'm going to pick 2 balls. Without replacement. And you ask, what is the probability of, say, a red and then a gray? Okay. Now we realize at this point that the probabilities change. The probability of a red is going to be 4/10. Okay. But then the probability of a gray ball now, well, now there are only 9 balls left in there. It's going to be 6/9. Okay. Remember, originally the probability of a gray would be 6/10, but now this probability over here is very dependent upon what happened in this event here. So these are not independent. So this is a pretty simple idea, and independence makes your life easy. Okay, it's easy to multiply 2 numbers together, and you don't have to worry about calculating anything else. Let's just consider one other example, and this is right out of the book. Suppose we had the following situation. I have an unfair coin. And by an unfair coin, let's suppose that the probability of heads is equal to 0.6, and the probability of tails is equal to 0.4. And let's suppose I am going to flip the coin I'm going to flip the coin 5 times. And I ask, what is the probability of 3 heads? Okay? Well, if we're going to flip the thing 5 times, first of all, we could think about the following. The probability, each of the flips are independent. So first of all, I could imagine that maybe I did something like this. Maybe I got a head, a head, a head, a tail, and a tail. Now each one of these are independent events. Any outcome here has nothing to do with the other ones. So this is going to be 0.6 times 0.6 times 0.6 times 0.4 times 0.4. But notice I say, what is the probability of 3 heads? Well, that's 3 heads, but here's another way to get 3 heads. I could have heads, tail, tail, head, head. And if I go ahead and calculate that, that's 0.6 times 0.4 times 0.4 times 0.6 times 0.6. Well, notice in both of these cases, it is 0.6 to the third times 0.4 squared. In other words, it's the same number here as it is for the same number here. Well, what I need to do is here's one way to get 3 heads. Here's another way to get 3 heads. Here's another way to get 3 heads. Okay, here's another way to get 3 heads. So what I have to do is I need to consider what are the number of ways and I have to multiply that by 0.6 to the third times 0.4 squared. Because remember, what's going on is the probability of 3 heads, well, it's going to be this for this one, and then it's going to be plus this one again for this one, and then it's going to be plus this quantity again for this one, plus this quantity again for that one. So I have to ask, how many ways are there to get 3 heads from 5 coin tosses? Well, this takes us back to something we saw a little bit earlier. There are 5 choose 3 ways to do that. And that's going to be times 0.6 to the 3 times 0.4 squared. And that is the answer to the problem.